My name is Seb, I'm from the University of Exeter and I work on planet formation. And in particular, I'm very interested in understanding how planets that look a little bit like the Earth maybe can form around other stars. So here's a picture of the Earth. No, here's a picture of the Earth. You recognize it immediately, right? It has the familiar continents, oceans, a nice atmosphere with oxygen. And the surface, you can see if you look closely, is riddled with life and is affected and changed by life continuously. The Earth is unique in that aspect. Right? The outer planets in the solar system don't even have a surface you can stand on. And most of the inner rocky ones, including Venus and Mars, are absolutely horrible, hostile places to live on. You don't want to live there for a long time, you won't survive. And this diversity of planets in the solar system has come about during planet formation when the solar system formed 4.5 billion years ago. Story went something like this. You start with a big cold cloud of gas and dust somewhere in the Milky Way, somewhere in some spiral arm. That cloud collapses and forms a new young star, the Sun in this case. And the Sun is surrounded by a swirling disk of material. And over time, over millions of years, the particles in that disk clump together and form the asteroids and the comets and the planets and all of that. So that's the reason, for example, why all the planets are aligned, why all their orbits are in the same plane, and why they all go around the Sun in the same direction. It's because they formed from a disk. And we know this story really well for the solar system because we have meteorites. There's one. I brought an actual meteorite. You are welcome to stop by and hold it after somewhere in the breaks. This bit of rock is older than the Sun, it's older than the Earth, it's older than the Moon, it's formed more or less together with the Sun. It's crazy. That's the solar system. Whoops. But what about exoplanets, right? Exoplanets are really far away. We cannot go there, we don't have samples of meteorites, but instead we can take pictures of these systems. Planet formation is ongoing in the Milky Way, so if you have a telescope that's good enough and you wait for a little bit, you can actually take a picture of a planetary system in the making. So this here is an image at radio wavelengths showing the formation of a solar system over 1,000 light years away. And the scale here, this is roughly the size again of the solar system. We can do a little bit better with the James Webb Space Telescope. And take actual spectra of these systems. This looks very noisy. I just wanted to give you a flavor of what this data looks like. All these wiggles here correspond to signatures of molecules like water, carbon dioxide, nitrogen-bearing species. And by studying how these molecules behave in space, we can try to figure out whether the planets that form will be sort of these barren, rocky hellscapes, or maybe they'll be places for some sort of weird alien biospheres, or maybe some of them will look like the Earth with an oxygen-rich atmosphere and semi-intelligent sort of critters crawling around. Thanks a lot.
Thank you. Is it attaching? There we go. Okay. Can you all hear me if I talk into this? Okay. My name is Dr. Sarah Moran, and I'm a scientist at the University of Arizona in the United States, and I'm going to talk to you about sunsets across the solar system and beyond. So we're going to start here. This one probably looks very familiar to you because it is, of course, Earth. We don't think we know yet of any of other places where we have these kind of industrial stacks sending smoke into the sky. But when you think about a sunset on Earth, what you're actually seeing is the signature of different particles that are suspended in the atmosphere. And the way that dust, and on Earth's case, that pollution interacts with light is what actually defines the colors that we see. And so if you think about the prettiest sunset you've ever seen, with all the reds and oranges and pinks, it's probably because there's more gunk in the sky that is absorbing the light from the sun before it reaches our eyes. If we go just a little bit further to our neighboring planet, to Mars, we see something that looks like this. And so the first thing you notice is that as the sun goes down, it looks really, really small compared to what we're used to here on Earth. And that's of course because Mars is further away from the sun than the Earth is from the sun. And the second thing you'll notice, I hope, is that this looks very blue. Mars, of course, is known as the red planet, so why the heck is this sunset a totally unexpected color? And it's actually for the same reason that the sky is blue on Earth. The particles, the dust particles that are suspended in Mars's atmosphere, are so small that they're actually scattering light the same way that the blue sky on Earth does. And so we end up with this very dramatic scene. Like I've heard a scientist say before that it's like you're in a smoky jazz bar, this faint blue cast across the sky. Now we're stepping even further into the solar system. This is not, unfortunately, a real image, but it's approximately what it would look like to us if we were there. This is Titan, which is the largest moon of the Saturn system. It has a very thick atmosphere, which you can see here in all these clouds. The sun is probably represented a little bit too big in this artist image, but the other thing you can see looming there is, of course, Saturn itself. And that is about as big as it would look in the sky if you were on the surface of Titan. And Titan has this intensely orange sky, this intensely orange sunset. And that's because it's actually very smoggy there. There's this process called photochemistry, where the sun is breaking up different particles, different gases in its atmosphere, and then they are recombining into a thick, smoggy thing, the way we think of as in polluted cities on Earth. So we end up with this gorgeous orangey sky on Titan. When we move to other planets beyond the solar system and exoplanets, we expect to see a similar diversity in colors that are completely dependent on the types of particles, types of chemistry, and how far or close they are to their star. So I hope to leave you with that and imagine just how spectacularly beautiful all of these planets can be. Thank you.
Hi everyone. Hi everyone. I'm Robin Liu, a second-year PhD student in Peking University, and today I want to tell you about how we can identify the composition of an exoplanet, and if you want to be rich, which exoplanet should we head for? As we can see, here is a photo taken by telescope, and we can see there are many dots on the telescopes, and for each dot there's an exoplanet. But it can make of different materials. Some exoplanets, like white dwarfs, is made of diamond. Wow, what if I can own one, right? And some others made of gold, but most of them are just covered by bare rocks. So if we want to be rich, which exoplanet should we head for? We cannot send a probe to any exoplanet. This aimless research is really expensive, right? So it's quite like this apple and banana right here. If we use telescope and see a red dot at here, we can think, wow, the apple is also red, so this planet is made of apple, possibly. And there is a banana here, and if we see a yellow dot, and we can say, oh, this planet could be made of banana. It's a cloudy day today, but next time when we see the sun in the sky, oh, it's yellow, right? And we can think, if we take a bite on the sun, it should taste like banana. And there's still one thing to go, because there are many fruits have red colors, right? Apple, cherry, and strawberry. But how can we distinguish those surface compositions? Luckily, by now we can distinguish between those red fruits. But at least we can know if we want to hunt for gold, it's yellow, right? We shouldn't head for the red ones. And that's all I want to share. Thanks.
Brilliant. And Michael, I think you're up next. Thank you. So if you click that on your laptop.
Oops. Okay, hello everybody. Thank you for coming. So today I'm going to tell you about the map that I took. Well, a very simplified map of a tiny, partially molten world. So this tiny world is 0.7 times the size of the Earth and 0.6 times the mass. So it's very, very dense. It's about twice the density of the Earth, about 10 times the density of water. And it's also very close to its host star. 1 year on this planet is only 0.3 days, so like 8 hours, which gives us a surface temperature of 1,700 degrees. So very hot, very small, very dense. Let's see if this plays. Oh, great, it actually plays. Okay, so this is how we make a map of an extrasolar planet. Here's a planet orbiting its host star. Now, our telescopes are not good enough to tell the difference between the planet and the star. Both of them are like kind of agglomerated into a single point of light. So we measure the brightness of this agglomeration, and we see something like this. This big dip is where the planet passes in front of the star. This small dip is where it passes behind the star, and we lose the light from the planet. So this dip tells us how bright the planet is, and the variation in between tells us the brightness of the night side and of every side in between the night side and the day side. Okay, so here's the real data. Let me move to the center. This is taken by the mid-infrared instrument on the James Webb Space Telescope. And okay, what can you conclude from this? One thing you can conclude is that the day side is very hot because this dip is very high. So the day side is about as hot as it can possibly be. Now the night side is consistent with 0 temperature, which means it's as cold as it can possibly be. The combination of the two means that the planet probably has no atmosphere. Because if it did have an atmosphere, it would distribute heat from day to night. The day will be cold, the night will be hot. So this thing is probably a bare rock with no atmosphere. All right, thank you for listening, and thank you for coming.
Fantastic. So I hope you enjoyed those talks, and we are going to be back in about probably 15 minutes or so on the hour. We're going to be here with our next set of talks. Come and tune in. In the meantime, the astrophysicists are floating around, so come and handle a meteorite, have a go with some of our demonstrations, ask any questions, have a chat, come on in and join us.